Hello and welcome to another session in physics. Well, in this particular lesson, we will be looking at the topic Electromagnetic Induction, Part 2. But before that, let us review the previous lesson. Welcome back. Well, in our previous lesson, we were looking at the electromagnetic induction part 1, where we talked about people like Lenz and Faraday's laws of electromagnetic induction and Fleming's law at the same time. So today let's focus more on things such as Fleming's right hand rule, which helps us to know how conductors move within a magnetic field. We also said that the current that has been induced in an electromagnetic field is called induced current, while the EMF is called induced EMF. Induced current can also be produced by moving a conductor in a magnetic field. The direction of such a current can always be obtained by applying what we call Fleming's right hand rule. Fleming's right hand rule states that if the thumb, the forefinger and middle finger are held mutually at right angles to one another, with the forefinger pointing in the direction of the magnetic field and the thumb pointing in the direction of motion of the conductor, then the second finger, which is the middle finger, will point in the direction of the induced current. That's what you can see from the image here. You would notice that the thumb, the way it's pointing to the motion of the conductor. The forefinger or the index finger is pointing to the direction of the magnetic field, and the middle finger or the second finger is pointing to the direction of the induced current. Now let's talk about an AC and DC generator. A machine that converts mechanical energy into electrical energy or electrical energy into mechanical energy is called a dynamo. When a dynamo changes mechanical energy into electrical energy, it is called a generator. But when it changes electrical energy into mechanical energy, it is called a motor or an electric motor. At this point, we have two classes of generators. We have the alternating current generator, which is the AC generator, and the direct current generator, which is the DC generator. The AC generator consists of the following: about 4 things. The first is that it consists of an armature. An armature is a rectangular coil consisting of a large number of turns of insulated wire wound on a laminated soft iron core. It is made up basically of a split ring that has been divided into 2 segments. Also, a magnetic field created by the curved poles of a horseshoe magnet or an electromagnet is an important feature of an AC generator. A third feature of an AC generator are 2 copper slip rings to which the ends of the rectangular coil are connected and they rotate with the armature. And then finally, the fourth part of a generator is 2 stationary carbon brushes which are made to press lightly against the split rings. That is exactly what we see here in the diagram. You notice the 2 magnets, the north pole and the south pole, their polarities respectively, and then you see the magnetic lines of force in the direction at which they are pointing, and then you look at the split rings, the 2 split rings, and then you look at the magnetic poles. This is an AC generator, and now we're going to explain these parts one after the other. Meanwhile, these are the carbon brushes respectively. Now, an AC generator can be made to produce a DC by replacing the 2 slip rings with a single split ring or commutator, as we've explained in previous lessons. And that's what you can see here. There are 2 split rings here, 1 and 2, but we just have to replace it with a single split ring that has been divided into 2 segments, and 2 of them insulated from each other That way, this AC generator can be made to produce DC. So the ends of the coil are then connected, one to each split ring or commutator segment. Now, when we talk about a commutator, we're simply referring to a current reverser because it reverses current. So when the armature coil is rotated, the commutator automatically switches each end of the coil from one brush to the other each time the coil completes one half of a revolution. As the current reverses in the coil after each half revolution, the connection between the coil and the brushes are reversed through the action of the commutator. So this is an example of a DC generator. Notice here that instead of having two split rings, what we have now is one split ring that has been divided into two segments insulated from each other. The AC generator and the DC generator are much the same. The only difference between the AC and the DC generator is the removal of the two split rings, removing the second split ring here and replacing it with one split ring that has been divided into two segments. Now let's talk about a transformer. Transformers are electrical devices that are used for changing the size of an AC voltage. Its main function is to increase or decrease the EMF of an alternating current. A transformer consists of two separate sets of coil, the primary coil and the secondary coil. The primary coil is predominantly known as the input winding of turns of wire, and the secondary coil is known as the output winding. The coils are wound round a soft iron core. The soft iron core acts to either increase and concentrate the magnetic flux within the core. It is also laminated. When we talk about lamination, we mean that it consists of sheets of soft iron insulated from each other instead of a solid block of iron. One thing that this lamination does is that it helps to reduce loss of energy in the form of heat due to eddy currents introduced in the core. Now, this is exactly what a transformer looks like. We have the primary winding, which is here, and we have the secondary winding, which is represented by the blue wires here. And then this is the transformer core, with there being a magnetic flux or magnetic lines of force all rotating. Now, still under a transformer, we want to look at the principle of operation here. You see, when an alternating EMF or an AC voltage is applied at the terminals of the primary coil, it gives birth to what we call E with subscripted P, which means the EMF of the primary coil. An alternating magnetic flux is produced in the iron core, which links or threads the secondary coil. An alternating EMF of the same frequency as that in the EMF of the primary coil is induced in the secondary coil by mutual inductance. Now, what do we mean when we talk about mutual inductance? When we talk about mutual inductance, we are simply referring to the flow of induced current or voltage in a coil due to an alternating or varying current in a neighboring coil. Then the total flux linking the two coils is proportional to their number of turns. So which means the bigger the flux, the bigger the number of turns, and vice versa. The induced EMF in the secondary coil depends on the EMF in the primary coil and on the ratio of the number of turns in each of them. So this is the formula that shows the relationship between the secondary coil and the primary coil, where the ratio of the EMF in the secondary coil to the EMF in the primary coil is equal to the ratio of the number of turns in the secondary coil to the number of turns in the primary coil. This is the main equations used to solve problems in transformers. Now, let's look at the workings of a transformer. In an ideal transformer with 100% efficiency, the power developed in the secondary coil is equal to the power developed in the primary coil. And we have ES, that is EMF in the secondary coil over EMF in the primary coil, equal to the EMF in the number of turns in the secondary coil over number of turns in the primary coil. It is also equal to the current in the primary coil and over the current in the secondary coil. Now, to use a transformer to increase an applied voltage, in other words, to use it to make the EMF in the secondary coil greater than the EMF in the primary coil, one thing we need to do is that the number of turns in the secondary coil must be greater than the number of turns in the primary coil. When such happens, we say that it has now turned into what we call a step-up transformer. When the number of turns in the secondary coil is greater than the number of turns in the primary coil, what happens is that the transformer is able to amplify or increase voltage, which results in a step-up transformer. Of course, in a step-up transformer, the primary current is greater than the secondary current, but the primary voltage is always less than the secondary voltage. Now, when it comes to transformers, there are about 4 energy losses in practical transformers. The energy losses, the first one, eddy current loss. Eddy current loss is energy lost in the form of heat, and this can be rectified by laminating the core of the transformer. We have the second one, hysteresis loss. Hysteresis loss is energy lost as a result of a reversal of the polarity of the transformer, that is, a reversing of the magnetization of the core. This hysteresis loss is reduced by the use of special alloys used in the core of the primary coil. So basically, it's all about redesigning the core of the primary coil. This will help to reduce hysteresis loss. We also have heat losses in the primary and secondary coils. As a result of resistance, normally when there is a level of resistance in an electric circuit, heat is lost. So as a result of this resistance in the primary and secondary coils, a level or some measure of energy is lost in the form of heat, electrical heat given by I squared R, the square of the current multiplied by the resistance in the coils. Now, what can we do to reduce this heat loss? We can do this by using thick wires or low resistance coils, or making more efficient designs of the kind of wires we use in constructing the transformer. And then finally, we have energy loss as a result of the leakage of the magnetic flux. Obviously, when there is a leakage in anything, it simply means that you have to patch that material. So the only way you can stop energy loss due to leakage of magnetic flux is by redesigning the core of the transformer. So this loss is reduced by a more efficient design and patching through the holes, reducing the gaps through which magnetic flux could leak. Okay, let's look at this example. A transformer has 500 turns in the primary coil and 300 turns in the secondary coil. If the primary coil is connected to a 220 volt main supply, what voltage will be obtained from the secondary coil, and what type of transformer is this? So the solution to this will be found using our general transformer equation. Alright, so we are looking for the EMF of the secondary coil, and we know the EMF of the primary coil is 220 volts. Number of turns of secondary coil is 300, and number of turns of primary coil is 500. So taking proportions and making the EMF of the secondary the subject of the equation, we're going to have 300 times 220 all over 500. So when we make our divisions and we make ES the subject of the equation, we're going to have 132 volts. Now, the second part of the question, what kind of transformer is this? So we have to ask ourselves, the ES and the EP, which is greater? So let's find out. The EMF in the secondary is 132 volts. The EMF in the primary is 220 volts. So here you discover that the EMF in the secondary is less than the EMF in the primary. So for that reason, this is a step down transformer. This is a step down transformer. Alright, so that's the answer to this question. Now let's look at finally the last slide, which has to do with power transmission. You see, power generated at power stations are distributed over large distances to consumers through metal cables. Power can be transmitted either at low current and high voltage or at high current and low voltage. The reason for this is because the metal cables through which the power is transmitted, they have a certain amount of electrical resistance. So when you transmit power at high current, it leads to a release of a large amount of heat, and this heat is lost in the form of energy. So it results in energy losses, which could lead to the melting of the wires and the conductors used in the transmission. Now, to avoid this, power is transmitted at high voltage and low current. Transmission of power at high voltage and low current is known as what we call high tension transmission. Low currents, on the other hand, lead to low energy loss. The reason for this is because low current requires thinner cables, there is no huge release of heat, and the cost of cable materials is considerably reduced if power is transmitted with low current and high voltages. So this is one significant advantage that high tension transmission has over high current transmission. Also, step down transformers are used to reduce the high transmitted voltages to lower voltages required in homes and factories. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.